Last time we looked at sequential circuit design. We developed state diagrams and state tables in order to describe these circuits. In this presentation, we'll take a deeper look at state machine diagrams and their applications. Here we see a Mealy model state diagram. Although this model serves well for very small designs, it often becomes cumbersome or unworkable for large designs. In particular, all 2 to the n combinations of input variables must be represented on the transitions from each of the states, even though the next state or output may be affected by only one of the n input variables. The output variables can also present problems. For each state or input combination label, up to 2 raised to the m output combinations must be specified, only though one among the m output variables is affected by the state and input values. The Mealy model is not very efficient in specifying outputs because of the need to combine transition and output control functions together. To overcome these problems, we'll use something called a state machine diagram. The main targets of the notation changes are to replace enumeration of input and output combinations with the use of Boolean expressions and equations. This will help us describe input combinations and the expansion of the options for describing output functions beyond those permitted by the traditional model. We'll need input conditions, output actions, and transitions for our model. An input condition as an expression is either equal to 0 or 1. An input condition on a transition arc is called a transition condition, or TC, and causes a transition to occur if it is equal to 1. An input condition that, if equal to 1, causes an output action to occur is called an output condition, or OC. For our new model, we permit output conditions to appear on the state, not just on transitions. We also permit output conditions that depend on transition conditions to appear on the arcs. This provides modeling flexibility in the formulation of corresponding state tables and HDL descriptions. For a given state, if a transition condition is equal to 1, then the corresponding transition represented by the arc occurs. For a given state transition, if all transition conditions are 0, then the corresponding transition does not occur. An unconditional transition always occurs on the next clock regardless of input values and can be thought of as having an implicit transition condition equal to 1. For example, state 0, the transition to S1 is unconditional. Outputs are handled by listing output conditions and output actions. The various forms of specifying the control of the output actions by state and output conditions are shown in this figure. Output conditions, if any, followed by a slash in the corresponding output actions, are placed at the end of a straight or curved line from either the state or from a transition condition, TC. Multiple output condition output action pairs are separated by commas. We classify output actions based on the conditions that cause them into 4 different types. More output actions depend only on the state. Transition condition independent TCI Mealy outputs are preceded by their respective output condition and slash. Transition condition dependent Mealy outputs depend on both the state and a transition condition. Those are TCD. And transition and output condition dependent TOCD output actions. In a given state, an output action occurs if it is unconditional, that's a more. TCI and its output condition OC is equal to 1. TCD and its transition condition TD is equal to 1. Or TOCD and its transition condition TC and output condition are both equal to 1. Any output action may be simply an output variable. It's also possible to have variables that are vectors with values assigned as the output. The final element that can appear on a state diagram is the binary code assigned to a state. This binary code appears in parentheses below the state name or at the end of the line drawn from the state. We need to perform checks to make sure that there aren't invalid next state and output specifications. For all possible input conditions, each state must have exactly one next state and have every single bit output variable with exactly one value, either 0 or 1, but not both. Put 2 constraints on the transition conditions. 1, the transition conditions from a given state must be mutually exclusive, and 2, the transition conditions from a given state must cover all possible combinations of input values. Likewise, we have constraints on output conditions. For every output action in a state or on its transitions, the corresponding pair of output conditions must be mutually exclusive, and for every output variable, the output conditions for state or its transitions must cover all possible combinations of input values that occur. Example 4.9 in the text covers how to check the constraints of the state machine depicted here. In particular, we check the 2 constraints for input and the 2 for output for each state. One of the text examples deals with the design of a mixing system that can add up to 3 ingredients to a large circular mixing tank. Mix the ingredients and then empty the mixed liquid from the tank. There are 3 inlets for the ingredients, each with an on-off valve. There are 3 movable fluid sensors in the tank that can be set to turn off the respective valves for the first ingredient alone, for the first and second, and for all 3 ingredients. The switch is used to select either a 2 or 3 ingredient option. The mixing system has a button for starting the operation and a second button for stopping the operation at any time. There's a timer for timing the mixing cycle. A manually operated dial that provides a starting value to the timer specifies the length of the mixing cycle. Timer counts downward to 0 to time the mixing. After mixing, the output valve is open to remove the mixed liquid from the tank. The inputs and outputs for the sequential circuit are given in this table. Before starting the operation of the mixing system, the operator places the fluid sensor L1, L2, and L3 in the proper locations. Next, the operator selects either 2 or 3 ingredients with the switch NI and sets the dial D for the mixing time. Then the operator pushes start to begin mixing operation, which proceeds automatically until the stop button is pushed. After that, valve V1 is open and remains open until L1 indicates ingredient level 1 has been reached. Valve 1 closes and valve 2 opens and remains open until L2 indicates level 1 plus level 2 has been reached. If NI is equal to 1, valve 3 opens and remains open until level 3 indicates 1, 2, and 3 have been reached. Next, the value on dial D is read into the timer, the mixing begins, and the timer starts counting down. When the timer reaches 0 as indicated by the signal TZ, the mixing stops. Next, the output valve is open and remains open until sensor L0 indicates the tank is empty. If stop is pushed at any time, addition of ingredients stops, mixing stops, and the output valve closes. The first step in the design is to develop the state machine diagram based on the description of the process and the problem statement. And it is the preset state. When start becomes true, we proceed to state fill 1. When L1 is equal to 1, we proceed to state fill 2. If we have the 3 ingredient option on, and L2 is equal to 1, then we proceed to state fill 3. Once L3 is equal to 1, or if we selected the 2 ingredient option, we proceed to the mix step and set the timer. Once the timer finishes, we empty the fluid from the tank. Note that we have the option to press stop at any time, which will take us back to the initial state. If we put this in a standard state table, there would be 256 columns, which is a lot. Instead, a table can be formed that enumerates rows for each of the following. 1. Each state with its unconditional next state and its TCI output actions and output conditions. 2. Each transition condition for each state with the corresponding next state. And 3. The corresponding TCD and TCOD output actions, the latter with output conditions. The entries in the non-zero outputs are either more outputs or TCD outputs. For the TCD outputs, Boolean expressions can be shared in the excitation and output equations. To this end, we define the following intermediate variables for use in the excitation equations and output conditions that are seen here. Using the one-hot state assignment listed in the table, assuming that each state variable is named with the state for which it is 1, the excitation and output equations are shown here. In the equation for init t plus 1, since all 6 states return to state init for stop, there is no need to specify any states with stop. X, Y, and Z are shared between next state and output equations. With the one-hot state assignment, the formulation of the equations is very straightforward using either state table or state machine diagrams. Thank you so much for watching. And if you're curious, there is another example of a sliding door in this section of the book if you'd like to